Hey, grade 11s, we've been taking a look at solids and liquids and gases and how they differ in terms of how the particles are moving and how far apart they are. We can see by looking at the pictures whether or not the substance contained in the flask is a solid, a liquid, or in the gas state. In the first picture, clearly our substance is in the solid state. The particles are vibrating on the fixed spots. So we have a definite shape. We've got a definite measurable volume. Adding a little bit of energy from the little burner at the bottom allows the particles to move apart and to move a little faster. The particles can now slide and roll past each other. This can flow. This substance will take the shape of the container that it's in, and we are in the form of a liquid. Adding more energy still in the final container, the particles are now vibrating fast enough to overcome the intermolecular forces that were holding them together. This is a gas, and in a gas the particles are moving very quickly, and when they hit each other there's enough energy that they bounce off each other with an elastic collision. No energy is lost when the particles collide. But again, I want to distinguish between the terms energy and temperature. I can see that the temperature is also higher in each of the flasks. But did the temperature rise evenly as we added more energy to each of the flasks? These pictures show us graphing the temperature change as we've added heat energy to a solid. And we notice that the solid changes from being to a liquid, and then eventually it changes to the gas phase. So we start with a solid, which eventually becomes a liquid, and then a gas. This happens as we add heat energy, and heat energy is measured in joules. Joules is a measure of heat, and it uses the symbol J. You notice that what we're graphing against the energy being added over time is the temperature, in this case in degrees Celsius. When we have a pure substance and we add heat to it, the temperature, as we would expect, will increase. However, as the substance starts to melt, there is no change in temperature. Again, once the melting is completed and we are in the state of a pure liquid, again the temperature is able to increase until it starts to boil. While it boils, there is no change in temperature. Assuming we can trap the gas and continue to add energy, at the point that it is a pure gas, the temperature will increase. Heat was added the entire time. The heat energy that I'm adding is either being used to cause the particles to vibrate faster, which is measured as temperature, or it is being used to overcome intermolecular forces and allow a phase change. During phase changes, there is no change in temperature. During a phase change, all of the energy gets used to overcome intermolecular forces, and any particle that has enough energy to start vibrating at a new frequency in the next phase leaves the phase that it's in. This is why in our past lectures we defined boiling as a cooling process. But the same concept occurs to the phase change between solid and liquid. This is a simpler diagram of the one you saw below. You'll notice that when we are in the state of a pure solid, or a pure liquid, or a gas, the temperature is able to increase. However, during a phase change, like melting or boiling, there is no increase in temperature. The diagram essentially looks like a staircase with only 2 steps, each step representing a change in phase. A diagram, a graph like this one, is called a heating curve. What would it look like, however, if I was removing heat energy? If I'm removing heat energy, our graph will look exactly the same, but backwards. Again, when we are in the state of a gas, in this case steam, or water, the liquid pure state, or ice, which is our solid pure state, we are able to see the temperature change. However, during the phase changes of condensation or freezing, there is no change in temperature. We never have a change in temperature during a phase change. Because the temperature is going down over time as heat energy is removed, we would call this a cooling curve. Again, it resembles a staircase, but has only 2 steps, one for each of the phase changes. We can actually calculate the amount of energy it takes to warm up a substance, whether it's solid, liquid, or gas stage, by using a measurement called specific heat capacity. Specific heat capacity is defined as the amount of heat it takes to raise 1 kilogram of a substance by 1 degree Celsius. It's important that we specify the amount of the substance that we are trying to heat and the degree we're trying to heat it up by. Obviously, it takes more heat to raise the temperature of the water in a swimming pool than it does to raise the temperature of the water in your kettle at home. As well, it takes more heat to raise a pot of water up to boiling point than it does to raise it by only 1 degree. So specific heat capacity tells us how much heat that we have in joules for each kilogram per degree Celsius. For water, the amount of heat it takes to raise 1 kilogram of water by 1 degree Celsius is 4,200 joules. This is defined as the specific heat capacity for water. Some things like water have very high specific heat capacities. Others, like sand, have much smaller ones. In the case of sand, we can raise the temperature of the sand, 1 kilogram of sand, by a single degree when it receives only 790 joules per kilogram degree Celsius. This is the reason why if you go to the beach and the sun has been shining on the sand and the water at the same time, the sand feels so hot and the water still feels cool. For every 790 joules of energy the sand received, it went up by a degree. But the same amount of water did not raise its temperature by a degree until it had acquired 4,200 joules, almost 5 times as much. The same thing happens in reverse at night. It takes the water a loss of 4,200 joules for the temperature to drop by a degree, but the sand will drop by a degree every time it loses 790 joules of heat energy. So this is why water heats up slowly but cools off slowly, and sand heats up quickly and cools off quickly. We can calculate energy in joules that is required to heat any substance up by knowing the specific heat capacity for that substance, multiplying it by the mass in kilograms and the change in temperature. This triangle symbol is called delta, and it means the change in. So this is the change in temperature in degrees Celsius. We won't be doing calculations of specific heat capacity in this course. However, the math is really quite simple. Remember, heat and temperature are not the same thing. Heat is energy. Temperature is the particle's response to that energy. We can also calculate the amount of heat that it takes to change the phase of a substance. We call this latent heat. Latent heat is the heat energy required for a substance to change phase. We call it latent because latent means hidden. When a substance is changing phase, even though I put energy in and I put energy in and I put energy in, the temperature is not changing. And that's because all of the energy that's going in is being used to overcome those intermolecular attractions. The particles aren't changing their vibrational response yet because they haven't moved far enough away from each other. Temperature is not increasing. So latent heat is measured in joules per kilogram and is used only during phase changes. Again, the symbol triangle means change. If you were to get burnt by steam or by water being poured on, boiling water being poured on your arm, you've probably experienced both at some point. Which one would be worse and why? Steam at 100 degrees Celsius or water at 100 degrees Celsius? Well, to answer that question, let's look back at our cooling curve. Let's consider where these 2 points would be on the curve. Steam at 100 degrees Celsius would be right here. Water at 100 degrees Celsius would be at this point. We can see that they are at the same temperature. Our body temperature is much lower on the continuum. When you get boiling water poured on your arm, it immediately starts to cool. The water at 100 degrees Celsius will cool down to the temperature of your arm, and all of that energy will get released into your arm, causing a burn. However, if you get steam poured onto your arm, first the steam has to condense, so all of this energy gets released into your arm, and the steam condenses to water. Then, as water, it needs to cool down. So you will receive twice as much energy being put into your arm and receive a much greater burn. Even though they have the same temperature, the steam has much more energy in it than the water does and causes a more severe burn. At the end of this lesson, I'm hoping that you are able to construct a heating or cooling curve for a substance. If I give you experimental data, can you identify where the phase changes, freezing, melting, boiling, condensing, are occurring, and label where the substance would exist as a solid, a liquid, or a gas? And can you explain why substances are heating up or cooling down at different rates? Also, explain why steam burns cause more damage than hot water burns and the difference between heat and temperature. I have on page 31 2 diagrams for you to label. On pages 34 to 37 of your work package, there is a workbook within a workbook where there are some readings and questions to answer based on what you've just read to help you understand these concepts. And at the remainder of your work package, pages 39 to 40, is the unit review for our Properties of Matter unit.